Last time we were working in section 3.2 with addition and subtraction of whole numbers. We had covered the addition part, and we'd also talked about some properties of addition in particular at the very end. We're going to pick up with a few basic addition and subtraction strategies, and then we're going to take a look at subtraction specifically. So these are a few strategies that you will see used inside of some classrooms, some curriculums. Some of them you may be familiar with them, you've used them yourself, and some of them you may be like, well, why would you do it that way? And that's okay. But if your curriculum does that and your state test tests you on that or something like that, you still might need to know it. So the first one's called the counting on strategy. What you do is you start with one value and you count up, should say the additional, not and additional, the additional amount of the other value. So imagine if you were doing something like 15 plus 3. You usually start with the larger value, 15, and then you add 3 more to it. So you start with the bigger number and you add up, count up to it. Doubles is one that is used more now than it has been in the past. Some children will learn their doubles before they'll learn their individual addition facts. So they don't start with the ones tables and then the twos tables and the threes tables. They learn what is 1 plus 1 and 2 plus 2 and 3 plus 3 and 4 plus 4 and so on. And they'll sometimes do it with a multiplication as well. My son actually brought home a multiplication doubles sheet the other day. So it's happening, even with the multiplication stuff. And the reason is because we can build on this idea. So if I know that 3 plus 3 is 6, then I can think of 3 plus 4 is simply 1 more than 3 plus 3. So I know 3 plus 3 is 6, I can add 1 more to it, and now I have 7. So that's the strategy or the reasoning behind it. Promise I didn't say you had to love it, but it is the reasoning behind that particular strategy. Making tens, which I like this one actually quite a bit. It's the idea of breaking something apart so that it makes tens. You can stretch this to actually thinking about what you would do if you were wanting to make hundreds or thousands or something like that too, if you were dealing with larger digits. So instead of thinking about 8 plus 6 is actually the 8 plus 6 strategy, breaking apart 6 into 2 and 4, because 8 plus 2 is 10, and then adding the 4 on afterwards. I know that for me, some of these strategies feel like, well, isn't it just easier to memorize 8 plus 6 is 14? And for most kids, yes, it probably is. But you're probably going to have at some point, especially those of you who deal with special needs situations, kids who memorization is really just not going to work. And so these are strategies to help with those kinds of issues, and they do lend you other options, so you can think about it from that perspective as well. A couple more are counting back. So this is like a subtraction strategy. If you were working on 15 minus 3, so you start with 15 and you count backward, kind of like when we were adding and we counted up, 15, 14, 13, 12, right? Tactile learners works really nicely to use your hands to do something like that. And then there's also the counting on strategy, which is very similar to counting back, but you start with the lower value and you count up. So for instance, if I were doing 15 minus 3, which is not a great example for this one, but if I were, I would start with 3 and I would count up until I got to 15. So 3 would be 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I counted 12. And that would be the counting up strategy. Obviously, it works a little bit better if the numbers are closer together. But that's the counting up or counting on, not up and on strategy. All right, so let's move into subtraction with a couple of those possibilities, sort of thinking about those. Subtraction is defined in terms of addition. And in fact, most kids learn it this way. And if you think back hard enough, or if you've seen used in a classroom recently, oftentimes you rely on the addition facts that the kids have memorized and taken addition tables and worked on the computer or whatever they've done on to actually establish what subtraction is. For example, if we have A minus B, we might ask ourselves, B plus what equals A? What do I have to add? So why is 6 minus 2 4? Well, it's because if I start with 2, I'd have to add 4 to it to get 6. Okay? So that's actually what subtraction is defined to be. And what I'd like for you guys to do is I'm going to pause while you guys move around. I'd like for you to go ahead and to get in your groups that you're going to work with as group work partner stuffs at the end of class. And we're going to be doing I'm going to show you some examples and then you're going to come up with some on your own. Okay, so we're going to look at 3 different models for subtraction. The benefit in knowing that there's different ways of thinking about subtraction is if you can identify that a student always misses a subtraction problem when it is presented in a certain way, then you know that the issue is not with mechanics of subtraction, but probably with the language of how the problem is set up. So I'm going to show you 3 different ways you can set up and think about a subtraction problem. The first one is the one that kids most naturally go to. If you were to ask a young child, what is subtraction? Probably they're going to say, it's takeaway, right? So this is the first model that we're encountering. Abby had 24 rocks. Eli sneaked into her room and took 5 of her rocks. How many rocks does Abby have now? So this is the idea of physically, I had the objects and some of them were removed, okay? And again, like I talked about last time, there's more than one way to write this down. I'm going to draw a concrete model for this, and I'm going to make rocks that are very circular, okay? So there's my rock. Do you like my rock? Yeah. And I need 24 of them. So draw yourself 24 rocks. And I kind of drew mine in this kind of a grid. There's absolutely no reason you have to do that. That's just for me to count. It was easier. Okay, so I have 24 rocks, and then physically what happened is I'm going to remove some of them. How many? 5. And so we can mark them out. We can, if we were working with kids that were first learning this object lesson, we might actually have rocks sitting on the desk, and we remove them and we count what's left. Okay? So you have the ability to manipulate this model, to use it and to show it in a variety of ways. But this problem, any way you do it, ends up working out to 24 minus 5. And if I count and look at what's left, how many were left? 19. And just like last time when we looked at some of these, we're going to make sure that as we write down answers to problems with context, we write down the contextual answer. So it's 19 rocks, not just 19. Okay? So the way in which I solved this was not what the model is. The model is the idea that I have something and then I remove. The second model is called missing add-ins. So Lelise needs to collect 10 leaves for a school project. She and Temeskin go out and find 8 leaves. How many more leaves does Lelise need? Okay, so in this situation, it did not say Lelise has 10 leaves and 2 of them blew away in the wind. It's not what it says. Right? She needs so many of them and she doesn't have all of them yet. So if I'm drawing a picture of this, we can draw how many leaves does she actually have? She has 8. Okay, so these are her 8 leaves. They're sort of kind of green. And of course she's missing some. So how many more would I have to draw in to show the ones that are missing if I need 10 of them total? I'd need 2 more, and you often will see your book draw them in as dotted. They're missing pieces. Okay, and then if I count all of them that are there now, of course there are 10 total that are in my picture, and the dotted part is my answer. So this answer would be, of course, 10 minus 2 is 8 leaves. I've drawn the concrete model. This is equivalent to asking, I wrote down, it was supposed to be 10 minus 8 is 2. I'm so sorry. We had 8, 2. There we go. It's equivalent to asking 8 plus what equals 10. You're missing the piece. So this particular model mirrors the definition of subtraction very, very nicely. It's a missing piece. All right, the third model is a comparison model. Madeline and Monique play basketball. Madeline scored 12 points. Monique scored 8 points. How many more points did Madeline score than Monique? This isn't takeaway. We didn't have one kid with points and the other one stole the points, right? It's not capture the flag. This isn't missing add-ins. It's not adding in a piece that's missing from somebody else's total. We're comparing. So for this one, I'm going to draw them as like points because it's points for a basketball game. So I'm going to actually draw this in. So the first character, Madeline, had how many? 12, right? So here's 12. And then I'm going to draw by comparison in the same way the points that Monique had, and Monique has 8. So if you sort of look at what's missing, obviously I'm missing those two. I'm missing one of these, and I'm missing the one where I crossed. So how many are sort of not there from Monique that were there from Madeline? There are 4. So I'm doing a comparison. It is 4 points. Now, of course, again, it's 12 minus 8. I mean, it's not like I'm not doing a subtraction problem, but the problem is set up in a very different way than a takeaway problem or a missing add-ins problem. So what I'd like for you to do next is I'm sorry, there's one more, my bad. Number line model. The number line model actually can use either of these 3 forms, the ones that I already did, but it always does it for objects that are not whole objects. So we did a number line model for addition, measurement or number line model there. And the idea is that it's something that can be broken down into pieces. We're not breaking it down, right? We're not working with decimals and fractions, but it's something that could have been. So in this one, Akeem drives 15 miles to the mall. As he's on his way home, his mom calls and asks him where he is, because obviously she didn't put tracking on his phone, which was her first mistake. So he states he's coming home and he has driven 8 miles so far. How far is Akeem from home? So we're going to draw a number line for this. And we have Akeem's home. That's his home. And we've got the mall. It looks kind of like a castle, but that's my mall. It's supposed to be big. And it says that it's 15 miles from one place to the next. So 0, 15. And Akeem tells us that he's driven 8 miles back. So the question is, my picture's not to scale, but the question is, how far does he have to go? So what is the answer to this question? It's 7 miles, not just 7, but 7 miles. Now, literally, especially if I'd drawn it to scale, we could count the spots in the number line. That would be a possibility if you want to think very concretely. We could talk about missing add-ins, this idea that something plus 8 equals 15, right? Think about it as a missing add-ins model. Either of those options would be possible. But either way we do it, any way we do it, we have 15 minus 8 is 7. Okay, now what I tried to say a minute ago is that you guys in your groups are going to create 4 problems. You do not need to solve them, okay? You're just creating 4 problems that would go in one in each category for these 4 categories. All right, take about 1 more minute if you're finishing. Still working? So this is audience participation time next. I want to hear some of what you guys wrote down, which means I need volunteers. And every group has to speak at least once. That's the rule. All right, so I need somebody to tell me, what did you get for your what did you write for your takeaway model? Volunteer. Do you want to volunteer?
Me?
Look like you were raising your hand. Were you just touching your hat?
Oh, yeah.
Oh.
But I can do it.
You want to volunteer. Fantastic.
Okay,
Thank you.
We put Daniel had 10 cookies. Sally ate 4 of Daniel's cookies. How many cookies does Daniel have left?
Very good. Sound good, guys? All right, I need one more example of a takeaway model. Who else wants to? Sam.
Sam has 5 toys. Her sisters took 2 of them away. How many more does she have?
Fantastic. Okay, an example for missing add-ins. Erica.
Yeah, $2 for coffee, but it costs $5 to buy. How many dollars do you have to borrow from a friend to buy the coffee?
Very nice. Okay, and then did you guys have one in the back?
Oh, yeah.
Okay. Yep, for missing add-ins.
Okay, Emma needs 10 toys. She finds 6 toys. How many toys does Emma still have?
Fantastic. Okay, how about comparison? I have 3 groups who haven't spoken, so one of you guys. Okay.
So for comparison, Seth ran 13 miles and Roxy ran 7. How many more miles did Seth run than Roxy?
Excellent. And you could call that a number line, a measurement model as well, because you used miles. And in some sense, you could do the one that you guys did with your money as well, because it has measurement abilities, because you can break the dollars down. So they're fine in the categories you went. I don't mean to say that they aren't, but they also could be considered that way. One more comparison model. Okay, Kira? Oh, sorry.
You have 4 Snickers, your sister has 6. How many more does she have than you?
Oh, how sad, right? Okay. Yes, so we compare the number of Snickers we have. Okay, so do you guys want to do your number line model? What do you have for that one? Yeah?
Okay, it's 30 miles from Shawnee to home. Hannah has to get a ride with Jacob, but he's only going 20 miles. How many more miles does she have?
Oh dear, is she going to hitchhike? Maybe.
I don't know.
All right, one more example for number line. One more group want to talk to us one more time. Everybody's said once, so. Okay, what do you have, Ariel?
We have Carrie lives 30 miles from her grandma. She's already driven 13 miles. How many more miles does she need to drive to get to her
Excellent.
grandma?
You guys all wanted to do miles. That's kind of funny. But yeah, we can break down miles, of course. You can break down other things too. So good job. Very good job. Okay, we're going to do one more piece of information today. This is about whole number properties for subtraction. And then I think I'm going to have to let you do your group work on your own because I don't want us to get any further behind. So the group work will be part of the homework. You still need to do it and do it the same way you would as our, on the front of the sheet of paper or whatever and add to it and all. You're just going to do it outside of class. We're going to talk about which of these following properties, there's 4 of them so far that we had for addition, which ones of them hold for subtraction. So the first thing we're going to talk about is closure. Remember, closure was the idea with addition that if I took 2 whole numbers and I added them together, I added together to get another whole number. The question is, does that work for subtraction? When I take 2 whole numbers and I subtract them, will I get a whole number? Not always is actually the correct answer. Not always. So sometimes yes, sometimes no. Can you give me an example when it doesn't work?
10 minus 15.
Fabulous. 10 minus 15, which would be -5. And -5, we're going to use some symbols you guys have seen, is not a whole number, right? So the closure property does not hold because there are cases for which I don't get whole numbers. Are there cases where I do get whole numbers? Well, yes, there are, but it doesn't happen all the time, so it doesn't hold in general. Commutative. Commutative is the idea that if I added the numbers, when we did it before, it didn't matter the order that I added them in. 2 plus 3 is equal to 3 plus 2. Does that work for subtraction? No, it does not. Can you give me an example?
13 minus 10.
Okay, so if I did 15 minus 10, I get 5. But if I did 10 minus 15, like I did on the previous problem, I get -5. And these 2 quantities are not equal. And in fact, that happens all the time for subtraction, right? The only time that they would be equal is if you did 0 minus 0, which is highly unuseful. All right, we don't need to do that. Okay. The next one is associative. So it might be kind of difficult to just think in your mind, maybe like you've done the last 2, of does this work? So let me just write one down. And actually the truth is that it doesn't matter whether you write it down the same one that I pick or not. So if I did 5 minus, I have no idea what I wrote down before. We'll do 3 minus 2 here. And we'll do 5 minus 3 and then minus 2. So with associative, you have to look at what's in the parentheses first. So 3 minus 2 is 1. So this first problem is 5 minus 1, which is now 4. The second problem starts out with 5 minus 3. What is 5 minus 3? 2. And then what is 2 minus 2? 0. And of course, 4 does not equal 0. Now, depending on what numbers you pick, I chose 5, 3, and 2, and I kind of did it with a little bit of strategy because I kept all the numbers whole the whole time. Depending on what numbers you pick and in what order, you might actually get negative numbers in the middle of that as well, which causes other problems. But the problem, of course, still is that the answer is no. It does not give me the same answer at the end. All right, people get tripped up on the last one, identity property. In order to have an identity property, what we had to do is it had to be added to either side of the number. So we said that 0 is the additive identity because 0 plus 5 and 5 plus 0 both equaled 5. Okay? The only possible answer for the identity here would be 0 as well. And the reason is because, for example, if I do 5 minus 0, I get 5. So it works, but the problem is it only works in one direction. 5 minus 0 is 5, but what happens when I switch the order? It's negative. right? It's negative 5, and that is not equal to the 5 I started with. It was supposed to both equal 5. Okay? So if there were such a thing as a half identity, we could go with that on this. There's not such a thing. This has no identity element, so there is no identity property for subtraction.